Okay, so now we're talking about end behavior models. End behavior models. Okay. So page 73, middle of page 73, end behavior models. So end behavior is basically when x goes to negative or positive infinity or negative infinity, what ends up happening. That is like the end behavior model. Okay. So let's jump into example number 6. Example number 6 says modeling functions for when x is large. Okay, let f of x equals to that and g of x equals to 3x to the fourth. Show that while f of g are quite different for small values, they are virtually identical when x becomes large. In other words, if x goes to positive or negative infinity. Okay? So if you go ahead and graph it, you should get the stuff that's on the left-hand side. If you look at the left-hand side, there are two graphs there. An A is when the window is small. You can see that the black one, which is y is equal to 3x to the fourth, is totally different than the blue one, which is where the others, which is the one that the more elaborate one. But if you take those two graphs and you stretch it out and go all the way to, what is this? 500,000 on the X window, you can see that they're virtually the same. You can't tell the difference. Okay. In other words, what the mathematicians say is that if we have this, and what else do we have? We had minus 2x cubed plus 3x squared minus 5x plus 6. If you go to infinity, this guy here ends up going to infinity so much quicker than the other ones here that this guy here dominates the function. And these guys here, the smaller ones, become negligible. Okay, so that's how you could think about it. Okay, all right. So also, blah, 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 and if you go ahead and divide those two and take the limit, in other words, if you take this and you divide it by the g of x, and you go limit as x goes to infinity, okay, what you do here is you divide the top and bottom by x to the fourth, and you're going to end up with okay, so I divided the top and bottom here by x to the fourth. Okay, so if I divide this by x to the fourth, I have that. Divide this by x to the fourth, I have that, and so on and so forth. As x goes to infinity, goes to 0, goes to 0, goes to 0, goes to 0. They all go to 0. And what do you have left? 3 over 3, which is 1. Okay, so in other words, this is a different way to say that if f of x and g of x have the same end behavior, then the limit of when x goes to infinity, f of x over g of x is going to be equal to 1. In other words, we would call the right end behavior is the same because we're going to the right end, right? We're going to the infinity end. If we took it to negative infinity, it would be the left end. If you looked at the graph on figure 2.13, you can see that the left end or the right end, the end behavior are the same anyway. So it doesn't really matter. So in this way, you can say that g of x is not only the right end behavior, it's also the left end behavior, which means that you can just say that the end behavior are the same. Okay. You flip the page, go to the top of page 74. There's a green box there. Go ahead and read that. Basically discusses what we just said. So it's the end behavior model, and the limit is to 1, limit is to 1 with the right end and the left end behavior, right? Okay, we talked about that. So let's see if we can do example number 7 here. Example number 7, find an end behavior model for that. So limit as x approaches an end behavior, doesn't matter. So let's go ahead and do a positive infinity one. I'm gonna have 2x to the 5th plus x to the 4th negative x squared plus 1 over 3x squared minus 5x plus 7. Okay, so what I would do here is I would just go ahead and limit x goes to infinity here. And I would go ahead and say what? This is the same as basically just this guy, right? Because as x goes to infinity, this guy is going to dominate the top and this guy is going to dominate the bottom. So this is basically the same as, which is the same as limit as x approaches infinity, 2 over 3x to the cube. So the end behavior is going to look like this. In other words, it's going to approach infinity, but it's going to approach infinity in a model or in a way that follows this. Okay. And that's number 7. So that was A, and in B we have 2x cubed minus x squared plus x minus 1, 5x cubed plus x squared, x minus 5. Okay, now unlike the first one, the top and the bottom have the same order polynomial. They're both to the 3rd. Okay, so again, the top one is going to be dominated by this, the bottom is going to be dominated by this, and I can say limit as x approaches infinity, 2x cubed over 5x cubed. So this is going to be 2 over 5. Okay. Or a different way to think about this is if you went ahead and divided everything, the top and bottom, by x cubed, right? Then it would be x goes to infinity, 2 5 right? If I divide the top by x cubed, I get this. If I divide the bottom by x cubed, I get this, where all of these are now, because x goes to infinity, they're all going to go to 0, and I have 2 over 5 left. So in other words, when the polynomial, the order of polynomials are the same, when you have the same like cube or same whatever here, then it becomes nothing more than this divided by this. Okay? So that's that. Let's go to example number 8. Example number 8 is a little more interesting. Example number 8, let f of x equals x, f of x to x plus e to the negative x. This is example 8. And g of x is equal to x. Okay. Show that g of x equals x is the right end behavior model. So this is kind of simple because it's giving you the right end model. It's giving you that. So if it is the right end model, what has to happen? It's the right, so we're going positive infinity. If it is the right end, that means that this guy here has to be 1. Okay, so that's what they're asking you to prove. So this is going to be equal to limit as x approaches negative infinity, 1 plus e to the negative x over x, which is the same as limit as x approaches infinity, 1 plus x e to the x over 1. Everybody see that? This is e to the x. Because this is e to the negative x, I just put this down underneath here, right? And as x goes to infinity, That goes to 0, so it's 1. You're given the conditions, you're given both functions, and you have to prove it, which is not that hard. The harder one would be if I give you this, and I say, find this. Okay, so that would be a little harder, right? Okay. That is the first one, while e to the negative x is a left-end model. So let's see that. So e to the negative x is the left-end model. So let's see if we can prove that. So we're going to left end, which means that x is now going to negative infinity. And now this should be equal to 1 if it is indeed the left-end model. So let's see what we got. We have a limit as x approaches negative infinity. I'm going to have x e to the minus x plus 1. Okay. So what's happening here? As e goes to negative infinity, this guy becomes e to the infinity. And this guy here is going to approach infinity much quicker than this guy approaches infinity, right? Because they're both going to go to negative. This is going to go to negative infinity. It's going to go to positive infinity, right? So it's going to go to 0, but this guy goes to infinity much quicker. So all you have left is 1. So there I proved that this guy is the left end behavior model. Okay. All right. And last but not least, we have example number 9, which gives you a little bit of trickery here. So example number 9, in example number 9, you are asked to find limit as x goes to infinity, sine of 1 over x. If you graph this, you end up with figure 215a. And we're going to approach, x is going to where? X is going to infinity. So as you can see, as x goes to infinity, it should be going to 0, right? Now that's graphically how you would do it. So how would you do this? How would you say algebraically prove that? The way you algebraically prove that is you would call, okay, so this is where the trick is. 1 over x, I'm going to call this as a large x. So I'm going to end up with sine of large x, and large x, since the small x goes to infinity, large x is going to go to 0. Right, which is basically, so sine of x, so if I graph sine of x, it's going to look like this. As x goes to 0, definitely I'm going to go to 0 here, right? So your answer is 0. Okay, so that's kind of a little bit of trickeration there. Okay. All right, that's all we have. I am done with 2.2.